Hi, I'm Michele from the Geometric Computing Laboratory at EPFL. Today I will present our work titled Computational Exploration of Multistable Elastic Knots. This is a joint project with Samara Ren and Mark Pauli from EPFL, Julian Panetta from UC Davis, and Ethan Greenspoon from the University of Toronto. Knots can be used to ensure safety when climbing or boating, in medical applications for surgical sutures, as decorations, and we can even find some knots at nanoscales, for example in DNA molecules. What happens if the wire in which we tie a knot is elastic? In the absence of friction, and when external forces are removed, the wire will tend to go back to its straight rest configuration, which minimizes its elastic energy. Numerous works have studied the behavior of such open knots to understand their mechanical properties from a theoretical point of view and in simulations. Different is the case of closed elastic knots, in which the ends of the wire have been connected together. A simple elastic loop will spring back to a circular configuration whenever deformed. If before closing up the wire we tie an overhand in it, we get what is commonly known as a trefoil knot. Physical experiments suggest that the preferred relaxed state of an elastic trefoil is a doubly covered circle, and several works confirm this claim. Gerlach and colleagues proved that in the limit of vanishing wire thickness, a doubly covered circle is in fact the global minimizer for the bending energy of a trefoil. Coleman and Swigon compute the analytical solutions of the equilibrium of an elastic trefoil with self-contacts. However, the method used in these works cannot easily be generalized to other knots. Gerlach's proof relies on bounds for the total curvature of a knot that are specific for the trefoil, while Coleman and Swigon's computations require knowing the location of self-contact points along the curve. Our work focuses on relaxing these requirements, and thus extending the study of equilibrium configurations beyond simple knots, and without any assumption on the contact set. Moreover, we are not necessarily interested in a single energy minimizer. We know from the literature that some elastic knots are multistable. The elastic figure 8, for example, is known to have at least two equilibria, one which is approximately flat, and another one which is more three-dimensional. One might then ask whether there are more local energy minimizers than just these two, and also if more complex knots can be multistable. Our computational pipeline aims at answering these questions. But how can the complexity of a knot be measured? As mathematical objects, knots are embeddings of the circle in 3D space. 2D diagrams can be used to represent 3D knots. A knot type is the set of all closed curves that can be deformed one into another without self-intersections, like, for example, the trefoil. Knot types can be classified by crossing number, namely the minimum possible number of double points in a 2D projection. The trefoil is the only knot type with 3 crossings, hence the code 3-1, where the subscript indicates a conventional ordering. There exists one knot with 4 crossings, the figure 8, 2 with 5, and as the crossing number grows, same does the number of knot types. We have, for example, 3, 7, 21, and 49 distinct knot types with 6, 7, 8, and 9 crossings, respectively. Equilibrium states of elastic knots correspond to local minimizers of a potential energy. We model the knot energy by a sum of an elastic and a contact component. We use discrete elastic rods and incremental potential contact to model both kinds of forces in a unified variational framework. To compute equilibrium states X star, we use Newton-based optimization. Our simulated relaxation converges to the expected equilibrium state for the trefoil and for the figure 8. To compute more equilibria of a given knot type, we need to sample closed curves having the desired topology. However, the space of closed curves is non-trivial to sample. Starting from the work of Tate in 1884, knots have been classified in tables according to their crossing number. The most recent knot table goes up to 19 crossings and contains more than 350 million knot types. This exponential growth suggests that a randomly picked closed curve will hardly have a given desired knot type. And even if it had, we wouldn't be able to know, as no efficient algorithm to tell knots apart is known. Generating random curves in R3 would then be unfeasible. This is why we restrict our sampling space to the cubic lattice Z3. We instantiate a curve of known knot type in Z3, and we apply local topology preserving random moves. We then simulate the relaxation, and then repeat the process for different initial curves. To analyze the results, samples converging to the same equilibrium state are grouped together using a metric that accounts for rigid motions and periodic reparameterizations. We discover that besides the few known equilibria, even the figure 8 has several additional metastable states with higher energy content. We confirm the validity of our discoveries by fabricating physical prototypes that show great agreement with the results of our simulations. Please refer to our paper for more details about our similarity metric, the hierarchical clustering, and additional comparisons with the literature. We also propose a set of novel recreational puzzles. The challenge consists of finding a deformation path that connects all the prescribed equilibrium states of a given knot, the 7-7 in this example. You're welcome to come talk to me and try solving the puzzle yourself during the interactive poster session. Overall, we simulate 3,000 different knot types with up to 12 crossings. The data we collect contain hundreds of thousands of equilibrium states. All the data and the code are publicly available on our website. One thing we were surprised to observe is that the majority of the stable equilibria we computed is close to planar. Our dataset of equilibria supports shape-based queries. For each equilibrium state, we compute geometric attributes and mechanical signatures that allow to efficiently compare elastic curves. Our algorithm retrieves the equilibria that are geometrically similar to a seed state, but have potentially different topology and different mechanical behavior too. Moreover, by filtering according to attribute values, we can select, for example, states that enclose a large volume and are approximately spherical. These states can be used to design jumping knots inspired by Joel Langer's work. Langer's knots come in a flat paper envelope from which they jump out as soon as it is opened. The challenge is to bring the knot back into the envelope. We exploit Alexander's theorem to design new jumping knots. The theorem states that every knot can be represented as a closed braid. A braid consists of a set of intertwined strands that, when closed up, result in a single continuous curve, which approximately covers a circle multiple times. If this braided state is unstable, then the knot will jump out of plane as soon as the external constraints are removed. With our method, we discovered a series of new jumping knots that have not been documented before. These and other multi-stable knots offer interesting opportunities for the design of self-deployable structures. To summarize, we presented a pipeline to simulate and analyze equilibria of elastic knots. We validated the correctness of our model by building physical prototypes, and we discussed some discoveries and applications made possible by our framework. Our pipeline is very general, and given enough computational resources, it can already be applied to the millions of elastic knots that haven't been studied yet. Some specific classes of knots, for example those with periodic structures, are natural candidates to be explored first. On the other hand, links, namely knots with multiple components, open the way for the design of even more complex systems, in which the mechanical behavior is dictated by the topology of an ensemble of simple elastic wires. So, if you want to help us explore this fascinating and yet largely unknown space, please visit our website to access the data and the code. Thank you for listening.